Okay, in this presentation we're going to look at Poisson random variables and confidence intervals for Poisson random variables. And this type of thing regularly pops up in insurance and financial maths and stuff like that, actuarial exams. Okay, it is assumed that the claims on a certain policy type arise as a Poisson process with a claim rate of lambda per year. So that's fairly straightforward there, okay? Lambda per year, Poisson process. For a group of 150 independent policies, just actually remember that n equals 150 and it's a large sample. The total number of claims during the last calendar year was 123. Just remember that. That helps us get a point estimate. Determine an approximate 95% confidence interval. So an approximate, okay. I'll just come back to that shortly, that it's sort of an approximated, that you might have to justify your approximation. Determine a 95%, an approximate 95% confidence interval for the true underlying claim rate during a policy. So let lambda denote the rate parameters. That's a typo. Okay, for a unit. Just to sort of say it's for one policy. Okay, not so clear here why I'm mentioning this, but if we actually look at other videos, presentations where I do similar sort of stuff, it's important to remember what lambda actually refers to. In this case, it's one particular policy, not 150 policies. That's a sort of little trick or little hazard that you have to watch out for when you're doing these Poisson random variables thing. What does lambda refer to? Is it one? Is it the group? You know, just that sort of thing. Let the total number of claims which arise under a policy can be denoted as x. So essentially what we're saying is this is a Poisson random variable, x. Okay? And the mean and expectation of a Poisson random variable in general is that the expectation equals the variance equals lambda, the rate parameter, okay, or lambda, or the mean if you want. Now we can use these to find the point estimate and the standard error, which is great. Now the mean number of claims per policy, okay, so x bar equals 123 divided by 150. That should work out to be 0.82, okay. And it's a large sample. Now, just actually, when I sort of said an approximate thing here, it's just good practice to sort of put in a little bit of a justification. Just actually some sort of sentence like this. We're dealing with a large sample. The sampling distribution is adequately approximated by the normal distribution. Just something like that, just to sort of say, you know, just sort of demonstrate your thought process here and why the word approximate there is relevant. Just to fill in your answer properly. Now, this is a sort of, this part here, this is a sort of stats 101. This is from hypothesis testing, standard error for a mean. Now, you should have sort of seen this stuff before when you're calculating standard errors for confidence intervals and hypothesis tests and stuff like that. Now, this format here is the one I usually would use myself, but this is also the equivalent, the correct equivalent there. Just restating it a slightly different way. Now, it's useful in this instance because what we have here is the square root of the variance divided by n, okay? And remember, the variance, that is lambda over n for this particular instance here, okay? Remember, we're dealing with Poisson random variables. So this sort of explains the structure a little bit better, what we got going on here. So this is our point estimate for the mean number of claims per policy. Sorry, I mistyped estimate there, but there you go. Is lambda hat, okay? Now, that's our point estimate, is the expected number of claims per policy, okay? Now, that's the mean, but also, again, just to re-emphasize, it actually also is our variance estimate as well, okay? So that's how we get from here down to here. We're using x bar in both cases. So x bar, which is 123 divided by 150, is 0.82, plus or minus 1.96 divided by, or times the square root of x bar divided by n. Now, just actually, if you're not clear where 1.96 comes from, it's the quantile for a 95% confidence interval, okay? Now, I won't explain it in this video because I reckon it's going on long enough. But if you are not familiar with that, how I immediately got from 95% confidence interval to 1.96, I suggest you go back to the basics of confidence intervals and hypothesis testing before you continue. Okay? So take it as an article of faith right now that the quantile is 1.96 for our confidence interval. Okay? So that this number didn't spring out of nowhere. It's because it's 95%, and you should know why. If you don't, you're going too far here. So 0.82 plus or minus 1.96 times the square root of 0.82 divided by 150. Essentially, what we have here is calculator work now. Okay, 0.82 plus or minus 1.96 times 0.0739. And essentially what we get there is 0.675 to 0.965. So that is essentially the answer we're looking for. Okay. Now, I'm not doing it here. Usually I'm quite fussy about stuff like this, but actually at the end, just sort of say this is our confidence interval. This is our 95% confidence interval. Just write it out a little sentence that the rate parameter, 95% confidence interval for the rate parameter for one policy is this. Just square it off properly. Okay, that's it. We'll leave it there. Boom.